Okay, so into the third speaker in the ASIC track just before lunch. We've got Graham Reith of MathWorks. He's the industry manager, communications, electronics, and semiconductors. The interesting chat with Graham earlier, who said that maybe MathWorks are now an EDA company, but we'll let him cover that in his talk. The title of the talk is Making the Most of Your MATLAB Models to Improve Verification. Graham manages the communications, electronics, and semiconductor business for MathWorks and EMEA. His technical background includes both hardware and software development workflows, in addition to representing the state-of-the-art of how MathWorks tools can be applied in EDA today. Graham always seeks to identify areas where MathWorks should invest further. So I'll hand over to Graham. Thank you.
Is there a clicker for the microphone? And is this working okay? Can you hear me?
Just move it up a bit.
Move it up a bit. Juggling microphones here today. Let's see. Is that okay? So if I'm talking like this, I guess that will come through louder. Yes, hello. Okay, so good afternoon, everybody. I'm aware of the last slot before lunch, so I'll make this brief, but hopefully this will also be very interesting for you and will stimulate some interesting discussion when we go into lunch. So that'd be good. So what's the motivation here? So really I'm looking at the role of MathWorks tools within semiconductor design. And in particular, one of the topics that's already been mentioned today is this idea of shifting left or left shifting verification activities in the development process. There's also been some interesting talk about agile development and ways in which we can perhaps be more dynamic in how we develop things that are going to get implemented into semiconductors. So that's one of the motivations. I'm going to talk a bit about that, both from a design point of view, but really from a verification point of view as well, in terms of how can we be quicker about our verification test bench development? How can we also make sure that things are connected across the design process? I'm going to talk a few technical topics. One is about the role of MATLAB and Simulink, which are MathWorks tools within this system development. It helps us with fixed point modeling, architectural modeling, things like that. But also how we can do things at the design stage in order to improve verification. So that was one of the topics that came up a little bit earlier on already. Was about how do we make, rather than design mindset, how do we help improve the mindset within the design stages and do better verification at that stage as well. A final thing I'll talk about how the verification environments might come out of MATLAB and Simulink, how we can actually reuse those within the verification activities themselves. So deployment, assisted Verilog, integration with UVM, and things like that as well. Okay? So first of all, this idea of shifting left in the design process. So this graphic here is a graphic that's been around for some time. It's well recognized within the sector. It's not a MathWorks graphic. But it essentially demonstrates the difference between where typical errors are introduced into a design process, which is typically at the specification and design stages, and where they're ultimately detected. And typically that's quite late on at the test and verification steps in the design process. So what's the objective? The objective is to try to move that detection of errors that we find there, to shift the scale of that, to actually bring it upstream. And from MathWorks' perspective, where we can help with through increased modeling and simulation, and to do some of that early at the design stage, so that by the time we get to implementation, we actually have less errors in the design to start with. So if you're working at verification, that's great, you've got less stuff to find. What that means to the overall design process, of course, is that you have less iteration based on bugs that could have been found earlier on. That will ultimately reduce the time to market. So where does this fit in? When we talk about within what MathWorks is developing and how our tools fit together, we talk about how our tools fit into the overall development process. So things that work from a sort of research at the concept stage, where people might be using MATLAB to describe the mathematics that makes a particular smart algorithm that they're embedding into their system. But ultimately it follows a lot beyond that. So how do I then take that algorithm, how do I then look at how it performs in the context of an overall system, whether that's pure digital, mixed signal, combination analog and digital, or a wider system context. Communication systems got RF components, digital software, all sorts of things going on within it. How do I look at the overall performance of the algorithm there and make sure that it is still fit for purpose? Then, once I'm happy with that, there's an implementation stage. How to go on and how do I then create that? So This graphic has lots of blocks and arrows on it. I'd like to simplify that a little bit. And I think about, the first stage, I'm thinking about what it is that I'm making. Let's make sure that I understand and characterize my particular algorithm I want to implement. But then there's the stage of how am I going to do that? Let's go through the detailed design and the architectural description of that. And then I'm in a position to then go ahead and actually make the thing. What we see is some organizations are very good at this. They're very good at taking that structured approach. Others may make the jump between that sort of high-level research, that what, to then directly go and do the direct implementation. The challenge with that is that you're doing a lot of that iteration down at an RTL level, and a lot of you're not actually discovering a lot of the bugs that will come as a result of that process. Parallel to this is that verification process. So initially, that validation of the requirements. Is the thing that I want to make actually what I should be making? If I then think about how I'm going to work it, let's figure out early if it's actually going to work or not. And finally, when I get to the actual implementation, perhaps the traditional verification task is, have I actually made that correctly, and is it all going to work when it's all synthesized in the facility? Okay. Part of the discussion earlier on was also about that agility. So if I talked about it in this way, we can think of a sort of a linear progression from specification of requirements through detailed design into implementation. It's been mentioned already that actually in practice, in the competitive semiconductor market, requirements change. One customer I was talking to was talking about 3 different changes to their requirements during the process of their development. So then, if at the top side here, if the requirements are changing, it's really critical that all these different stages are closely and tightly integrated together. Because if something changes here, that might affect that, ultimately that affects that. So really what can make these projects successful is the ability to adapt and respond to those requirements, update your design, and yet still be able to produce an implementation that we know is correct to bring out the door. Okay, so typically when people think of MathWorks, they think of us being up here in that research space, MATLAB, floating point, very much focused on the mathematics. We have a lot to play in this detailed algorithm design stage too. Typically tools like MATLAB, Simulink, bringing together architectural descriptions of their models, looking at the behavior of analog and digital components together, looking at the detailed timing, control logic, the different microarchitectures that actually describe the implementation. That's also a key thing that we're bringing into this development process. So building up that, if I can do this here, building up this system design gives you great visibility into the how you're going to do this thing. We do also have tools to then help take that how and actually then get to the point you can just generate the RTL for it, or for software to generate the C for that implementation. I'm not going to talk about that in this session, there's enough time, I want to focus on the verification angle here, but that's very much a technology's reality. One of the interesting things, though, coming out of that technology is the customers who are already using that, one of the things that they've told us is that because they're doing their development at this level, where they're doing that structured, detailed model of how they want to implement something, they can do a lot more different trade-offs of different architectures they might want to use for the implementation, and as a result, end up with something better than what they've done previously. So they find that the quality of results that they get is extremely good. It's better than their previous hand code because they're able to try different architectures. So that's an additional benefit of actually doing that modeling up front. Is not only are you finding the bugs, you've also a little bit more able to adjust your design and do something better for the implementation overall. On the verification side of things, you've got that flow back to the requirements. You're verifying against those requirements initially. And then you've got a detailed design. And you can reuse that detailed design later in your verification. I want to talk more about that towards the end of this session. What does this mean? Well, I've talked about doing this more effort in the detailed design. So here is some breakdown from a real customer project where they looked at this type of technology. And what we can see, if I look at that green bar, this is where they're doing that more detailed modeling and simulation up front for any downstream implementation and verification activities. So we can see, compared to previously, where that was a relatively small portion of their design, they've increased the effort in that. as a result, the further stages downstream are significantly reduced because they're not doing that same iteration that they've been doing previously. They have to do it at that later stage where it is less productive. Somebody asked a question earlier on about organizational shifts. I think this is one of them, is that if I look at how organizations are set up to run projects today, being able to spend more time figuring out what you're doing before you start writing code can represent a challenge to some organizations, because they may measure things based on how many lines of code they've written. Well, in that case, you're measuring the wrong thing, because really it's better to figure out what the right design is before you then start writing code at all. But yeah, just as a sort of measure on what we can do with, well, some of the challenges in terms of organizational adoption, that's certainly part of it. So if I look at where customers are getting benefits out of this today, out of this model-based design approach, we do run sort of large events with our existing customers to get their feedback on various topics. And one of the surveys we ran out of this was, where do you see benefits out of this approaches? And the three top things that came out were requirements deficit reduction, design defect reduction, and coding defect reduction. So that represents the first three bars in that chart, as I showed you earlier on. But if I break this down further into whether people had just started using the tools and typically using them for a part of the project versus people who are using the tools and spanning multiple different organizational groups, then we saw another difference. So between the people who are perhaps optimizing their process, looking to get that level of integration, they saw that requirements defect reduction was significantly greater, design defect, again, similarly, and coding defect, particularly with the use of these automatic code generation tools, was eliminated virtually altogether. So that was something that was also quite revealing about this. Okay. Someone was talking about unit testing earlier on. I think this is also very relevant here. So how we use MATLAB tools as a golden reference, typically they are broken down into a test bench, a simulation test bench, around the component which you're actually implementing. Thank you. Now, depending on the what it is you're developing, you might start off with something that is the description of what it is, the floating point model, and then add more detail to that to make it bit accurate, cycle accurate, and a full architectural description of exactly how you're going to do that. But if I look then within that model, essentially you've got the test framework and you've got the implementation thing. And when people build models within our tools, they should be doing both of those things and have those things separated out. Not everybody does, but they should do that. So at that model level, we also have tools to help improve the test benches. And this is where I think it's helpful to bring the verification mindset up to the design stage. So tools such as Simulink Verification Validation, Simulink Design Verifier, will help us do things like look at the coverage within the models. What is it we're actually testing? That helps to make sure we uncover more bugs at that early stage. And indeed, if we don't have enough coverage, then yes, we can generate the tests in order to produce the coverage. Again, doing that at the design stage. And yes, absolutely we should be checking that the results of that are actually what we expect. Otherwise, as I said, it hasn't got much meaning beyond identifying bits of dead code. So yes, absolutely we should check the results of that. So as an example, this is a model of an LTE modulator and detector. Again, something that could get taken through into RTL if you wish. But when I run my system simulation, the kind of metrics I get back are looking at things like the spectrum, figuring out if I can pull out the right cell ID. That's the sort of system level metrics that I'm interested in that give me overall performance measurements. But if I then look within a particular portion of that design, there's a particular section within some of the detection algorithms that are quite logical. So how would I look at that and see, well, what is it I've really tested here? And this is where coverage tools can look at us and say, well, have you independently toggled each of these logical conditions, and can I demonstrate that? And then we can generate reports to say, actually, no, we need to spend more effort on these parts. And then to go a stage further, to generate the tests to then achieve that full coverage. So these, again, at the model level, are tools that we can use to help bring that verification mindset up to the design level. Then move on to another topic. So beyond just improving the quality of testing and improving the models in which we're developing, how do we reuse this stuff? So if we have models that describe what our implementation is, we could use that as a specification that I hand over to the verification team. So I don't know how many of you guys might receive such a specification today, and then use that specification to recreate what you already have within your whether system Verilog or other verification languages. Again, somebody made the point earlier on. There can be bugs in your verification environment as much as there can be in the implementation code. So how can we make this process a bit more efficient? So one thing we can do is actually use the models to then generate the components that you might use in the verification environment. So from the models, you can either generate the test data, the models that produce the test data, or models of the algorithm itself to use as your behavioral reference within that environment. We can generate C. C is very portable. You can integrate that with all sorts of different verification environments. For System Verilog, because it's widely used, we've actually automated the process of generating wrappers for System Verilog to bring in that C code. So that's something that we've already implemented just to make that life a little bit easier. It's automated. It's an automatic translation process. You're not going to have those manual coding errors in generating that, generating those reference models, and there's something that can be very readily and easily integrated into that. So as an example, if I've got my System Verilog UVM environment, something I could be doing, if I wanted to create a implementation of my checker within my scoreboard, would be if I've got some MATLAB code already that implements some of that, or in a few lines of MATLAB code, I can create my reference model, but then create something I can plug in directly into my UVM environment. So MATLAB code for my checker may look something like this. You've essentially got about 5 lines of functional code there, also some of which is converting real and imaginary into complex data types. Taking my FFT and maybe then looking at the difference between my FFT that's coming from a design of the test, and then quantifying the difference with that. One command will then generate us a bunch of files. So it will generate the C, it will generate the wrapper, and something I can directly integrate. So I've got my C code files that get generated, my DPI interface, and if I like, a System Verilog module if I want as well. I could either take the System Verilog module as is, or in this example for integrating in with UVM, I could just use the import functions directly into whatever UVM framework I like in order to integrate those two things together. So 5 lines of MATLAB code, easily adjusted. This saves us a lot of work, but importantly, it not only is saving us work, but it's also giving us models earlier, so we can directly export that, and we've got that connectivity across the design process because it's connected to that original source that we might be using for our verification. Easy to update bullet. Again, I think back to my agility point. If my design is changing, okay, here's a very quick way I can update my verification models in order to capture any changes that have happened in my requirements and changes that have happened in my design. Okay. There are a couple of other things I will mention. One is for particular components in my design, I may choose to bring my RTL into MATLAB and Simulink. We have technology to work with RTL simulators to bring that into Simulink. And similarly, we could use FPGAs to do that as well. So if I think about, instead of going out from MATLAB and Simulink and exporting it into these other environments, there is the option to go the other way. That does help perhaps with visibility around particular components and looking at the behavior of a function in the context of a larger system. Again, if you want to know more about that, do come and grab me at lunch and I'll explain a bit more about the details there. So moving on to next steps. If your focus is on verification, then I think a good question to ask is, how can I reuse models that I might have elsewhere in my organization in this verification step? It saves you effort, but it also improves the overall development process by establishing that connectivity across the two. And when I think about that overall design flow, again, that left shift, we've already spoken about some of the benefits that's bringing. How do I improve modeling fidelity earlier on in my process? So not only do I get better models, but also I get less bugs in the design when it actually comes to me anyway. If I sorted that out earlier, that will help overall what it is that I'm testing. If you want to know more, there is stuff on the web. So again, in your notes, you can look this stuff up or indeed you can contact me. I'd be very happy to have a more detailed discussion on any of this, and I can have you.
Thank you, Gun.
Otherwise,
Thank you very much.